Hi physics students, so today we are going over the answer key for the review worksheet, and this is just talking about the forces between positive, negative, and neutral objects. So between a positive and a positive, they are like charges, and so they're going to repel. So I'm just going to put R for repel. Positive and negative are opposite charges, so they attract. And then positive and neutral objects also attract, because even though the neutral object has an equal amount of protons and electrons, the polarization of the neutral object causes the negative charges in this object to attract to the positively charged object, number 2. So same process goes for the next row. Object 2 is negative and positive, opposites attract. Negative and negative repel, and negative and neutral are also going to attract. So regardless of the charge, positives and negatives attract to neutral objects. Same goes with a neutral and a positive, and a neutral and a negative, but for a neutral and a neutral object, if they have no charge to them, then nothing happens. So this one is nothing. Here it says two objects repel. One of them is positive. Well, in order for objects to repel, the other one has to be a like charge, so it's also positive, and that's the only option to have repulsion. Two objects attract. The object is negative. The other object has to be positive because opposites attract, but it can also be neutral, because we know that neutral objects also attract charged objects. A piece of clothing fresh out of the dryer has picked up a positive charge and is attracted to your uncharged hair, which is polarized. Sketch the distribution of charges and describe why the attraction happens. So first, we've got our piece of clothing. So this is my rough drawing of a shirt, and the shirt has a positive charge. Now this is a person, and the person has hair, and we know that positive charges attract negative charges. And since the person is neutral and I've included 6 negative charges, I'm going to include 6 positive charges. And so the positive charges are going to repel, it's going to try to get as far away from the positively charged shirt as it can. So it's going to move all the way to the right. So why does the attraction happen? Well, the polarization causes these negative charges in the hair to move as close to the positive shirt as possible. And the positive charges are going to move all the way to the right, away from the positively charged object. And because the negative charges are moving close to the positive shirt, that's the attraction that's happening between the negative charges in the hair and the positive charges in the shirt. It's due to polarization, which is the effect of charges separating based on attraction and repulsion. So the next one talks about types of charging. Charging by friction is caused when you rub two objects together. So causing electrons to transfer. Now, based on the electron transfer, it is dependent on the two objects rubbing. Some objects like to be more positive and other objects like to be more negative. It's based on a scale that we call the triboelectric scale. And when the rubbing occurs, the object that likes to be more negative is going to absorb the electrons from the other object. And that's what causes one object to gain a negative charge and the other object to gain a positive charge. So the example we used in class, we took this rubber tube and we took some kind of fur, and when we rubbed them together, they would become charged. And I can't remember exactly what happened, but the rubbing caused, let me use a different pen, caused electrons to transfer from one object to the next. And we know that only electrons can transfer, not protons. So charging by conduction, this is a transfer of charges through contact. And a good example of that is when we had the Van de Graaff machine. Let's say the Van de Graaff was a positive charge. Well, when someone goes and touches the Van de Graaff, when that person touches the Van de Graaff, then the positively charged Van de Graaff is going to pull electrons into it, so the electrons transfer. And basically, the electrons are gained from the ground through the person and into the Van de Graaff. The charge by induction, so this one is a transfer of charges without contact to the charged object. A perfect example of this would be our electrophorus lab. So in the electrophorus lab, we had a, I think it was positively charged. We had a charged styrofoam plate, and then we took a neutral pie tin, which also had a insulating cup to hold it, so there were no transfer of charges. But what happens there is, even though the pie tin doesn't touch the styrofoam plate, it's going to cause polarization, and the polarization is going to cause whoever's touching it. So let's say a person touches the metal pie tin, it's going to cause the electrons from the ground to transfer through the person and be attracted to all these protons that are polarized to the top of the pie tin. So that's what we call charging by induction. In this next example, a Van de Graaff charger is turned on and it has a negative charge. Explain why you get a shock if you touch it. So the negative charge on the Van de Graaff is going to, that should be a negative charge, is going to cause charges when it is touched. It's going to cause these charges to travel through your body and into the ground. So anytime you have something called grounding, which is excess electrons traveling through your body and out your body, that's when you experience a shock. The next one says you stand on a stool and have the generator turned on. So this is based on grounding. You stand on a stool and have a generator on. Your hair stands up. Why don't you feel a shock? Well, the shock only happens when the electrons travel out through your body and out of your body. So when you're standing on an insulating stool, what ends up happening is you've got your Van de Graaff, and the person here is standing on an insulating stool. the Van de Graaff is going to have all these negative charges, and when you touch it, all those negative charges are going to transfer into your body, but they don't have any place to go. So you're just going to feel these negative charges all over you, and it's going to feel like some sort of energy kind of exuding from your body. Your hair is going to stand on end, but you don't actually feel a shock because these electrons don't have any place to go. So the hair standing on end is all the electrons on the tips of your hair trying to repel each other, because like charges repel, and so that's why your hair stands on end, but why you don't feel a shock. Let me write it down. It's a build up of charge causes the like charges, whether it's positives or negatives, to repel, but can't transfer out of your body. So that is the reason why you don't feel a shock and why your hair stands on end. The last one is explain why, if you touch the generator with a plastic pipe instead of your hand, you don't feel a shock. But if you touch the hand of someone who just touched it, you will. Well, the reason why is because if you touch it with a plastic pipe, you're going to stay neutral because the plastic pipe is an insulator and it doesn't allow charges to transfer through you. So if I draw the person with the pipe, let's say this is the plastic pipe, they stay neutral. The person who touched the Van de Graaff, and I'm assuming that this person is standing on an insulating stool, the person that stands on the Van de Graaff is going to have some excess charge all over them. And so when you touch each other, the excess charge is going to transfer away from that person and onto your body, because your skin is a conductor, whereas the plastic pipe is not. So by touching each other, the electrons transfer, and when the electrons transfer into you and also through you because you're touching the ground, that's when the feeling of shock occurs. Here it says 2 charged spheres are held near each other as shown. The force between them is 20. What will happen to the force if the distance is halved? So this is something that you want to understand about forces. First of all, we discussed the equation. So this is the equation. K is a constant. Q1 is your charge. Q1 and Q2 are your 2 charged objects over distance squared. Now, we never did any calculations with this Coulomb's law equation, but what we did do is proportion problems. And what we realized is that force and distance squared, or R squared, which they use R for distance, they're inverse proportions, and they're an inverse squared proportion. Whereas force and charge, I use Q, because that's what's in your physics helper. This worksheet uses C, is a direct proportion. So as charge increases, force increases. As distance increases, force decreases by a factor squared. So let's go ahead and do these problems. I've got a force of 20, and it says that the distance is halved. Well, if the distance decreases, then the force is going to increase. Now, what I like to use is a division squared, but you could do this multiple ways. So instead of dividing by half, I'm going to divide by, and I don't have much room here, but 1/2 squared, and 1/2 squared is a quarter. So let me just simplify this. 20 divided by 1/4, and then I'm going to multiply by the reciprocal. 20 times 4, which is equal to 80. So as my distance increases, my distance decreases, my force increases. What will happen to the force of the distance when it is doubled? Well, here's my force. If it doubles, I'm going to divide by 2 squared because it's an inverse square proportion. So that simplifies down to 20 over 4, which is equal to 5 newtons. So increase in distance decreases my force. What happens to the force if the charge is 4 times larger and the distance stays the same? This is a direct proportion. So you're just going to multiply 20 times 4 is equal to 80, and that's your new force. And what will happen to the force if both C1 and C2 are each 4 times larger? So for this one, you have to multiply it twice because both charges are quadrupling. And that's going to give me 320 newtons, I believe. The next one says, what will happen to the force if C1 is 4 times larger and the distance is doubled? Well, first we're going to take our force and multiply it by 4 because that's a direct proportion with the charge. And the distance doubled is an inverse squared proportion, so I'm going to divide it by 2 squared. Well, 4 and 2 squared cancel out because it's 4 over 4, and I end up with the same value of 20 newtons. All right, so in problem number 6, it shows a positive and a negative charge. So this is our positive and negative. And it says the black dots represent 4 locations. Draw the direction and relative strength of the electric field at each point. Hint, it will come from the combination of forces on a positive charge at each location. So these little dots we can consider positive test charges. And we want to think about how that positive test charge is going to move as we think about its location from the big positive and the big negative charge in red and blue. So what we know is like charges repel. So this positive test charge is closest to the positive red charge, and so that's going to move to the left. And we know that for this one in the middle, the positive charge is going to move away from the red charge and toward the blue negative charge because opposite charges attract. Same with this test charge. It's closest to the negative, so it's going to move close to that negative charge. And then this object right here, it's going to want to do 2 things. One, it's going to want to repel the positive, but also attract to the negative. So if you want to think about the direction it's going to be flowing in, it's going to be somewhere in the middle, probably straight out in this direction. So what we are looking for is what the electric field is going to look like based on the movement of a test charge anywhere in the vicinity of these 2 charges. And so I'm going to use green to represent the electric field, but the electric field always points away from the positive and into the negative. And if it's at an angle, it'll curve up and back in, up and back in. And these little loops are going to get more and more spread out. But the closer they are to the charge itself, the stronger the force is going to be, because obviously distance is a huge factor in the strength of the electric field here. So all my arrows should point out of the positive and into the negative. Now, electric field lines, I already answered that question. Electric field lines always point away from a positive charge and toward a negative charge. And a neutral object has no electric field because there's no charge to it. And we know that neutral objects don't attract or repel anything unless there's a charge near it. So no electric field. Next, we're going to get into defining different characteristics for a circuit and listing the units. So I'm going to list the unit first. For electric current, the unit is A for amps, and the definition of electric current, it is the rate in which charges, oops, I forgot an H there, in which, let me just erase that, in which charges flow. The next one is voltage. Voltage is easy, that's measured in volts. And voltage is the amount of electric potential energy held in a power source, which allows objects to do work. Work to be done. And in the case of a light bulb, it allows an object to exude light energy. Resistance, that's measured in ohms, and that is what slows down the flow of charge. And power is measured in watts, and that power is directly related to brightness. And the equation we use for power is current times voltage, which means that power is directly related to the rate in which the charges flow, as well as the amount of voltage that is in the power source. Parallel circuits, it's a circuit in which each device or light bulb or resistor, so I'm just going to call it device in the circuit, is directly connected to the power source. And then a series circuit is when each device in the circuit is connected to the power source through one loop. Now, a short circuit is when there's no resistance at all. Circuit with no resistance. And what happens is there's too much current that flows through the circuit, and that can cause fire. It's one of the main dangers in a household, and often it's just because somehow people don't realize that there is a circuit there in which the current can flow, and it'll always flow through a wire with no resistance before it flows through whatever device you're trying to connect it to. So it's basically a circuit with no resistance where too many charges or too much charge is flowing through it. Okay, in each of the following circuits, each resistor is 2 ohms and the voltage of the battery is 6. The current in the circuit at point 1. So before we do this, I'm going to go ahead and draw a VIR chart. I think that's most helpful. And so I'm going to add in all the information that's given. It tells me that the total voltage is 6 volts. That's my battery. And it tells me that each resistor is 2 ohms. And what I know here is that in a series circuit, all I have to do is add all these guys together in my resistance, and I will get the total resistance. So here it's 6. And if I look at the bottom row, if I look at the bottom row here, I can see that my total voltage and my total resistance can be used to solve for my current. So I'm going to add this here, my VIR chart. Current is voltage divided by resistance, so it's going to be 6 divided by 6, which gives me 1. And then what I know about a series circuit is that my current, whatever it is in the beginning, is going to be what it's going to be all throughout each resistor. So from there, I can automatically solve for my voltage for each resistor, which is I times R. So it's going to be 2 times 2, 2, 2, and 2. And just to check, all this voltage should add up to 6, and I get that. Perfect. Okay, let's try green. I'm going to do circuit B, and I'm going to put that table down here. Obviously, you don't have to do this. You can do it, answer the question step by step, but I already know that by doing this, I'm going to get all my answers to the questions in this problem. So I'm going to, again, I'm going to use the values that are given, which are 6, and my resistors. I'm going to use red to fill in what we need to solve for. So the total resistance in this resistor is going to be my inverse equation. So 1 over 2 plus 1 over 2 plus 1 over 2 gives me 3 over 2, but I still have to flip it, and I end up with 2/3 of a total resistance. So that's going to be my answer here. So in order to find my current, my total current, I'm going to have to take my voltage, 6. So this is voltage divided by my resistance, and 6 divided by 2/3 is going to be, I'm trying to squeeze this in, 6 times 3/2. And so I end up with that reducing to 3, and I get 9. So I kind of squeeze the work down there, but hopefully you can see how it equals out. The other thing I want to fill out is the fact that I've got a voltage of 6, and for parallel circuits, the voltage across each parallel resistor is going to be the full voltage drop of 6. And then from there, I can just do my division. I know current is voltage divided by resistance, and that gives me 3 all the way down. And if I add up my current, I should end up with 9, and 3 plus 3 plus 3 is equal to 9. So that works out perfectly. Now let's look at what we're trying to solve for here. Current at point 1. The current at point 1 is the total current coming out of the circuit. So if I look here, my total current for A is going to be 6, and the total current for B is going to be 6, or sorry, I'm looking at the voltage. Sorry, the total current is 1, and then the total current for B is 9. So it just says to compare and contrast. And so all I'm going to say is that the current for B is greater than the current for A. the voltage drop across R1 in each circuit. So for R1A, it's 2. For R1B, the voltage drop is 6. So this is actually something you can see right off the bat, but a parallel circuit is always going to have a greater voltage drop than a series circuit. So B is greater than A again. The current through R1 in each circuit, so I'm looking at this guy and this guy, and the current in a parallel circuit is greater than the current in a series circuit. And now we're looking at total resistance. So total resistance is 6 for A and 2/3 for B. So that gives me the fact that the resistance for A is greater than the resistance for B. Okay, so in this part, it asks for the total power, and we learned that the power equation is I times voltage. And so I'm going to look at the total voltage and the total current for each one, and it's pretty clear that the power is going to be greater in a parallel circuit. So B is going to be greater than A. And power is directly related to brightness, right? And we know by experimenting and also playing around with our electric house projects that our parallel circuit is brighter than the series circuit. So that's a common concept that you're going to want to know. If these were light bulbs, another type of resistor, what would happen to the brightness of the bulb if R3 were removed while keeping a closed circuit? So for A, if R3 were removed, that reduces my total resistance. And by reducing my total resistance, I increase my current. So that's going to make this circuit brighter. By removing a resistor here for B, I'm actually removing a whole pathway in which my current can travel. And so that slows things down and actually causes my resistance to get larger. And so by doing that, I end up, I increase my resistance and I decrease my current, which makes things dimmer. And just to get a good calculation out of that, let's say we drop this guy out, I would have a total resistance of 1/2 plus 1/2, which is equal to 2/2 or 1. Obviously, if you take the inverse of 1, you're still going to get 1. And 1 is a greater total resistance than 2/3. So high resistance, low current is directly related to brightness, or power, which is directly related to brightness. So these are your answers for letter F. Okay, in this next problem, we are going to simplify this circuit. So I always like to draw it as a vertical circuit, which you can or don't have to use whatever method works best for you. And I start off with 24 volts. I've got 5 ohms here. I've got 4 ohms and 12 ohms in my parallel circuit, and I've got 8 ohms at the bottom. So what I'm going to do first is I'm going to take this parallel circuit and I'm going to find the equivalent resistance, or what we call the total resistance of that circuit. So 1/4 plus 1/12 gives me 3/12 plus 1/12. I end up with 4/12, and if I flip that around, I end up with 3. So I'm going to, I don't have room, but I'm going to say this is 3 ohms. Okay, what I'm going to do, because I don't have a ton of room, is I'm just going to go ahead and erase this, turn it into a series circuit, and I'm going to use red because I am now replacing it with a 3 ohm resistor. what's great about that, and I just realized here I didn't even have the right voltage. This is 24 volts. What's great about that is now I have a series circuit. 5, 3, and 8 are along the same line. I just add them together and I end up with 16. To get my total current, all I have to do is take my total voltage, which is 24, divide it by my total resistance, which is 16, and I end up with 1.5 amps. In this next one, this is a pretty complicated circuit. I start off with 60, and as I split it off, I end up with my 10 ohm resistors on one side, so I'll label that. And then I have an 8 ohm this is the 16 ohm resistor that splits off into 2 parallel resistors of 8 and 8. So looks like a funky circuit, but we are going to simplify this down into something much nicer. First of all, the 8 and 8, I want to look at this and simplify it down to an equivalent resistance of 1/8 plus 1/8, which is 2/8. I flip that and simplify it. I end up with a total resistance of 4 ohms. So if I had a room, I would just draw another circuit, but I don't. So I'm going to take this, I'm going to substitute in my new resistor of 4 ohms, and that's going to give me 2 circuits in series. So now I can simplify this and this. 16 and 4 simplify down to 20. 10 and 10 also simplify down to 20. So I'm going to write down the equivalent resistance here. And I'm going to make this 20 ohms and 20 ohms. Now that I've simplified that, I can see that it is now a parallel circuit. And again, with parallel circuits, when I simplify, I just take the reciprocal. That should be a 20, not a 12. That simplifies down to 2 over 20, which if I flip it ends up as 10 ohms. So that's my equivalent resistance, or my total resistance. When I want my total current, I just take my total voltage, divide it by my total resistance, and I get 6 amps. So I got my total voltage from the battery and the total resistance from the answer above. So that gets you your resistance and current. This last unit, the electric current, is conventionally shown as flowing from positive to negative in a circuit. The actual flow is opposite, moving from negative to positive, because protons can't move. Well, when I showed you a video of how batteries worked, I always talked about how there was a buildup of positive charges, buildup of electrons on the positive charge. So it didn't quite match what the sign of the battery says, but it still applies that the electrons transfer out of what they call the positive side and into the negative side. So the convention was opposite of what is actually happening, but this is how we draw the diagram of a battery for it to make sense. So don't forget, you've got some labs and concept builders that you want to look over. Make sure that you study all of this, and if you have any questions, contact your teacher. All right, good luck.